Welcome to the module. In this comprehensive session, we will bridge the critical gap between theoretical high voltage physics and practical field safety through five core modules. Module 1 establishes the foundation, covering the core principles of high voltage field stress and insulation coordination. Module 2 transitions into compliance, focusing on mandatory electrical safety standards NFPA 70E and IEEE 1584. Module 3 details arc flash hazard analysis and mitigation strategies to protect personnel. Module 4 unpacks the physics of Paschen's law and dielectric breakdown in gas, liquid, and solid insulators. Finally, Module 5 explores advanced HV measurement techniques, resistive dividers, CVTs, and Rogowski coils. When designing high voltage systems, understanding the absolute voltage magnitude is only the first step. The true challenge lies in managing electric field stress, or voltage gradient, measured in kilovolts per millimeter. In an ideal uniform field, the stress is distributed evenly between flat conductors. But in reality, conductors have sharp edges. Electric field lines naturally concentrate at these sharp points, drastically increasing the local voltage gradient. If this localized stress exceeds the surrounding dielectric strength, breakdown begins. This is why insulation coordination, smoothing geometries to manage these peak stress zones, is an absolute necessity. In high voltage engineering, understanding exactly when a gas will lose its insulating properties and allow current to flow is absolutely critical. This brings us to Paschen's law, a fundamental principle that describes the breakdown voltage of a gas between two electrodes. The law mathematically states that this breakdown voltage is a nonlinear function of the product of gas pressure and the gap distance. Let's visualize this with the Paschen curve. On the x-axis, we have the pressure distance product, and on the y-axis, the breakdown voltage. Notice the distinct U-shape. As the product decreases, the voltage initially drops to a critical lowest point known as the Paschen minimum. At this specific point, the gas breaks down most easily, posing the highest risk for electrical arcing in high voltage environments. However, decreasing the pressure further into a vacuum sharply increases the breakdown voltage again, a principle heavily utilized in vacuum circuit breakers. Transitioning from gases, we must examine liquid and solid insulators. While gases can often recover their dielectric strength after a breakdown, liquids and solids behave very differently under high voltage stress. In liquid dielectrics, such as transformer oil, breakdown is typically initiated by impurities. Moisture and microscopic particles align with the electric field, forming conductive bridges known as streamer mechanisms that eventually bridge the gap. Solid insulators face a more severe threat. Under prolonged electrical stress, localized partial discharges cause molecular degradation. This creates hollow carbonized channels within the material, a phenomenon called electrical treeing or carbon tracking. Unlike liquids, which can sometimes circulate and self heal, solid breakdown is permanent and cumulative. Once an electrical tree breaches the insulation, catastrophic failure is inevitable. In high voltage engineering, protecting expensive substation equipment from unpredictable electrical transients is a critical design priority. This approach is known as insulation coordination. Insulation coordination involves carefully selecting the dielectric strength of all system components to minimize damage from lightning strikes and switching surges. A fundamental metric here is the basic insulation level, or BEIL. The BEIL represents the maximum impulse voltage that equipment like a transformer can safely withstand. To ensure the BEL is never exceeded, we deploy surge arresters. By clamping the overvoltage and diverting it to ground, they maintain a strict margin of safety. Safety in high voltage environments is not optional, it is a fundamental requirement. The invisible nature of electrical hazards demands a rigorous, standardized approach to protect personnel and equipment. The foundation of this approach is NFPA 70E. This standard establishes the essential safe work practices, defining approach boundaries and identifying the specific personal protective equipment required for qualified workers. Alongside it is IEEE 1584. the definitive guide for performing arc flash hazard calculations. It provides the mathematical models necessary to accurately predict incident energy under various fault conditions. Together, these two standards form the gold standard for electrical safety. IEEE 1584 quantifies the exact hazard, while NFPA 70E dictates how we must act and protect ourselves against it. When working near energized high voltage equipment, NFPA 70E establishes specific approach boundaries to protect personnel from shock and arc flash hazards. At the center is the exposed energized conductor. The distance from this point determines the level of hazard and the required safety measures. The outermost boundary is typically the arc flash boundary. When crossing this line, personnel must wear appropriate personal protective equipment to prevent thermal burns. Next is the limited approach boundary, which is a shock protection zone. Unqualified personnel must stay outside this line unless continuously escorted by a qualified person. Finally, the restricted approach boundary is the closest distance. Only qualified personnel with proper training and insulated tools may cross, as it is treated like direct contact. While NFPA 70E sets the boundaries, IEEE 1584 provides the rigorous mathematical models needed to calculate the actual hazard. It predicts the incident energy of an arc flash, which directly determines the required personal protective equipment, or PPE. To perform this calculation, engineers must evaluate four critical variables. First, the bolted fault current, the maximum available short circuit current. Second, the arcing time, which depends on how quickly protective devices clear the fault. Third, the electrode configuration, since the physical arrangement of conductors alters the arc's behavior. And finally, the working distance between the worker and the potential arc source. By accurately assessing these variables, we transform theoretical risks into quantifiable safety protocols. An arc flash is a catastrophic electrical explosion, far more destructive than just a bright flash of light. When an electrical fault occurs across a gap, the air becomes ionized, forming a highly conductive plasma arc that bridges the conductors. This plasma arc generates intense thermal radiation, with core temperatures reaching up to 35,000 degrees Fahrenheit, hotter than the surface of the sun. Simultaneously, this extreme heat instantly vaporizes solid copper busbars. As solid copper turns to gas, it expands to 67,000 times its original volume in a fraction of a second. This rapid explosive expansion creates a devastating pressure wave, blasting molten metal, shrapnel, and toxic gases outward with immense force. Understanding these extreme physical phenomena is the critical first step in effective hazard analysis and mitigation. When mitigating arc flash hazards, we rely on the hierarchy of controls. This systematic framework prioritizes the most effective safety measures over the least. At the very top are elimination and substitution. The most effective way to prevent an arc flash is to completely de-energize the equipment before any work begins, eliminating the hazard entirely. When live work is unavoidable, we implement engineering controls. This includes installing arc-resistant switchgear or using remote racking systems to physically separate the worker from the blast zone. At the bottom of the hierarchy are administrative controls and personal protective equipment. PPE, such as arc-rated suits, is strictly the last line of defense. PPE does not prevent an arc flash, it merely improves survivability. True safety starts at the top. In high voltage engineering, directly measuring system parameters presents a fundamental challenge. You cannot simply connect a standard multimeter to a 138 kilovolt transmission bus. Doing so would immediately result in catastrophic dielectric breakdown and severe arc flash hazards, as standard instrumentation is only rated for low voltage environments. To safely monitor these systems, we must bridge the gap between utility scale power and sensitive control electronics. This requires specialized high voltage transducers. These devices serve two critical functions. They provide precise proportional scaling of the voltage, and they ensure absolute galvanic isolation to protect both equipment and personnel. When measuring high voltages, we cannot connect standard instruments directly to the bus. Instead, we use a resistive voltage divider to safely step down the voltage to a measurable level. The circuit theory relies on a simple series stack of high precision resistors. The high voltage side R1 absorbs the bulk of the potential, while the low voltage side R2 provides the output signal to our meters. According to Ohm's law, the output voltage is a precise fraction of the input. This makes resistive dividers highly accurate and exceptionally stable for measuring direct current and power frequency AC systems. However, every physical resistor has inherent parasitic properties. At very high frequencies, such as during switching transients or lightning strikes, stray capacitance alters the impedance ratio, introducing significant measurement errors. Capacitive voltage transformers, or CVTs, are the essential workhorses of the utility grid at transmission voltages like 138 kilovolts. Standard magnetic transformers are simply too massive and expensive. CVTs solve this using a smart two-stage process. First is the capacitive stack, the tall insulator structure. Inside, capacitors C1 and C2 act as a voltage divider, stepping the massive grid voltage down to an intermediate level. Below the stack sits the base tank containing the electromagnetic unit, or EMU. Here, a step-down transformer further reduces the voltage to a safe 120 volts for your relays and meters. Crucially, a tuning reactor cancels out the phase shift caused by the capacitors, ensuring an exact scaled replica of the grid. When measuring massive transient currents, like those in an arc flash, standard current transformers often fail due to core saturation. The solution is the Rogowski coil. Instead of a heavy iron core, it uses a helical coil of wire wrapped around a non-magnetic air core. As alternating current flows through the central conductor, it generates a changing magnetic field that induces a voltage in the coil. According to Faraday's law, this induced voltage is directly proportional to the rate of change of the current, or d/dt. By passing this signal through an integrator circuit, we reconstruct the original current waveform perfectly. With no iron to saturate, it safely measures extreme faults. Choosing the right high voltage measurement tool depends entirely on your target, steady state voltage, utility grids, or transient fault currents. Let's compare our three main technologies. First, we have resistive dividers. Primarily used for DC and low frequency AC, they offer exceptional precision but suffer from high frequency stray capacitance. Next, capacitive voltage transformers, or CVTs. These are the standard for utility scale AC grids. They safely scale down massive transmission voltages, but they are physically bulky and strictly limited to AC. Finally, Rogowski coils. These are engineered specifically for extreme transient currents, such as arc flashes. Because they use an air core, they never saturate, offering a critical safety advantage. Matching the instrument to the hazard is essential. To conclude our comprehensive module, let's recap the three critical pillars of high voltage engineering we've established today. First, mastering the physics of high voltage. Managing field stress and understanding dielectric breakdown mechanisms forms the foundation of effective insulation coordination. Second, rigorous safety compliance. In these unforgiving environments, strict adherence to NFPA 78 practices and IEEE 1584 arc flash calculations is mandatory. Finally, precision measurement. Deploying the right tools, from CVTs to Rogowski coils, ensures accurate system monitoring. Integrating physics, safety, and measurements equips you to approach high voltage systems with technical confidence and uncompromising safety. Before we conclude this module, let's review your understanding of the critical concepts we've covered today. Ask yourself, do you know the exact incident energy for your specific equipment? According to IEEE 1584, this calculation dictates your PPE rating. When evaluating gas insulated systems, do you know where your operating pressure and gap distance sit relative to the Paschen minimum? Are your solid insulators showing early signs of carbon tracking? And are you using the correct tools like a Rogowski integrator to measure transient fault currents without saturation? Take a moment to reflect on these questions. Your ability to apply these principles directly impacts the safety and reliability of your high voltage operations. Thank you for completing this module on high voltage fundamentals and safety protocols. Stay safe.